Okay, so is everyone on Jamboard now? I think I'm in the wrong Jamboard. No, I'm in the right one. Okay, so we're gonna meet on Jamboard, so let's go to slide 1. All right, so today is the second last lesson for this electricity topic. And looking back at how we started it, we have a very simple circuit. And we try to give the example of what happens when you decrease the length of the wire. So in this case, we have to assume something about the wire though. We have to assume that there is resistance along the wire. Which is a strange thing to assume because normally this is what should be happening always, that all the wires have a level of resistance. But now we're doing an assumption where they have resistance. So it's a bit confusing because normally you assume that there isn't, but now I'm telling you that there is in order to help you understand this example. So if we keep the voltage the same, in other words, the power source, what's going to happen to the circuit as we decrease the length of the wire?
Repeat that one more time.
So again, we're keeping the power source the same. We're assuming that there's resistance along the wire. What's going to happen to the circuit as we decrease the length of the wire?
It will get harder.
So as you decrease the length, the wire heats up, and that's essentially what happens, right? And then we talked about before that the short circuit, all it is that the length of the wire is so short that it heats up to a high level of degree, then it just melts. So why does this happen though?
Because all the energy has to be used before returning back to the battery.
Good. So that's actually a law we mentioned before, but we never gave this law a name. That's why I wanted to start the lesson with this particular example. So Max said that all the energy that you gain at the power source has to be lost in a complete circuit, more or less, right? All the energy needs to be used up.
Yep.
Now, the period 2 class, they actually came up with a very, I call it a bourgeoisie term. What's the term for energy being used up? Something happens to this energy. The energy...
Converter?
No. It starts with the letter D. Okay, nobody knows. Dissipates. And technically that's how the law is written. So all the energy that's gained at the power source dissipates throughout the entire circuit. Or another way of saying it is all the voltage gain has to be equal to all the voltage drop along a circuit, a closed circuit. Now this law, it gets credited to a scientist named Kirchhoff. So we call this Kirchhoff's voltage law. But as you can see how difficult it is to write Kirchhoff, because the name has a very high chance of getting it spelled, the spelling wrong. So instead is commonly known as KVL. So Kirchhoff's voltage law, all it says is that all the energy that's gained at the power source needs to be all the energy lost throughout the closed circuit. which is why we explained that this phenomenon happens, right? Because if you gain some energy at the power source, the energy is used up along the closed circuit, and if you change the length of the wire to make it shorter and shorter and shorter every time, then the energy is more concentrated, which means it heats up more until it eventually melts. Make sense? Any questions on that part? No? So again, this is Kirchhoff's voltage law. Now let's go to the next page. All right, so now what we did with the wire, we created a split, or we branched it out. So this, you might have to recall from your earlier studies. What happens to the current when the current meets a junction? The current is said to split. You guys are kind of low energy today. What's going on?
What is split equally?
Is it because I didn't want to release my private information?
Yes, but what is split equally?
Oh, Max, you're always one step ahead of everyone. Okay, so in this case, we're not putting any resistors. Resistors are things like light bulbs. So we're only considering the wire. And I try my best to draw it very symmetrically. So if we're talking about the same material, and that material gets split, and the split still contains the same material, and the length is the same, then we can say that the current actually splits equally or unequally.
What if the length is different? How would that affect the current? Because assuming everything is exactly the same, it should be exactly even, no?
Yeah, so there are cases where you could split the current and one side will be longer than the other. So current likes to follow the path of least resistance. Kind of like, is that like a Buddhist mantra? Path of least resistance?
No, Buddhism is middle road, middle path.
No, Buddhism is life is about suffering, and to avoid suffering, you have to choose the path of least resistance, I think.
What? Well, so Buddha was a liberal, life of pleasure.
The life of pleasure. Something like that. You quit. You don't seem convinced by my studies of Buddhism.
Oh well, I'm not Buddhist, so I don't know.
Oh, see, I didn't want to assume that you were, but I did anyways.
Cancel.
All right, so in this case, the current, when it meets this junction here, it's still going to split. But because the resistance is not the same on both sides of this branch, then the current actually splits unevenly. So current does not split 50-50. But when the resistance is the same on both branches, then the current splits 50-50. But regardless of these two scenarios, what happens as the current joins back into a single path? Does the current get lost, or does the current add up again to the value that it was before?
It adds up again, right?
Yeah, so let's put some numbers because otherwise it gets complicated, right? So let's assume that the current going in is 2 amperes. And since it's 50-50, 1 ampere on the left, 1 ampere on the right. And when they recombine, you get back 2. Likewise with the other example, if we have 2 amperes and they split, so let's say 1.5 amperes and 0.5, when they meet back again, they form the 2 amperes of current. So what can we conclude from this example? What happens to the current when it meets a junction?
The outcome will be the same.
The outcome will be the same. Actually, that's pretty good. That's kind of how I remember it. So I like to remember as the current in equals to the current out. So I in equals to I out for junctions. Right? That's kind of what you meant?
Yes.
Okay, so this turns out to be another law. So this has to be true in all cases of circuits. And guess who came up with this law? The same guy from before.
Chris.
Kirchhoff. And because this deals with current, they call it Kirchhoff's current law. But over time, people are so mean because they couldn't spell his name. So instead, they write this law as KCL. So imagine going through all the work to come up with a law and no one can spell your name, so they just give you the acronyms. This is a sad life.
Oh.
Yeah, you know my period 2 class, I have a student named Aaron because you don't know if it's with 1 A or 2 A's. So his name would just be called the A law. Imagine how sad that would be. This is joke. Ha ha ha. Alright.
Oh.
Tough crowd today. I feel like I'm talking to myself.
Funnier jokes.
You know why? Because I started off the lesson by saying it's the second last lesson. You're like, wow, I can't believe my time is up with such a great teacher. Yeah, I know how you feel.
What?
All right, let's go to slide 3. All right, so in grade 9, if you were in the school back then, there's only 2 types of circuits that you looked at. Wait, sorry, I'm going to redraw this. Hey, what's going on? There's terrorism going in my page. So the 2 basic type of circuits that we look at is a series circuit and a parallel circuit. Oh, I had to think about that for a moment. But now, yeah, you know, I ordered my lunch from Food Panda, and now I know there's another company called Ninja, and I didn't know about this because Food Panda quality is going down. Like I couldn't finish my food; it was so bad. So bad.
I don't think Panda makes food.
Which one?
So you threw the food away?
I don't think Food Panda makes the food, Mr. Morales.
No, I didn't throw it away. I still ate it, but then I didn't eat all of it. Then I gave the rest to the Wildcats.
Why is it Food Panda's fault?
Because when you go to the restaurant, you get 3 tacos, but when you order it, you get 2.
That's not their fault.
That's.
But you said it's so bad you couldn't even finish, so why would you want 3 instead of 2?
Yeah.
Oh, that's true too, right? Because psychology. Yeah, maybe that's.
You know what? The 7 deadly sins is gluttony, Mr. Morales.
Well, you got to pick your sin, right? So might as well pick one that doesn't hurt so many people. All right, so now remember the assumption that we made before? We said that the resistance along the wire was present, but now from now on when we look at circuits, so either series, parallel, or mixed, we're going to assume that the resistance along the wire is negligible. Negligible. I probably spelled that wrong. All right, so let's analyze this together. So we're going to be analyzing by looking at the current, and then we're going to look at the voltage. So when we look at a circuit connected in series, all the current from the source as it travels through, how's that going to be related to the current at the first resistor? Now, you could call light bulbs resistors. So you could say, what happens to the current when it goes to the first resistor? Is it going to change or stay the same? Hey, stop, focus, focus.
What's the question?
Okay, so we have the current from the source, and as it travels and it comes across the first light bulb, what happens to the current? Does it stay the same, increase, or decrease?
Decrease.
Increase.
And as the current continues moving on to the next light bulb, what happens to the current again?
Decreases even more.
And then once it goes back to the source, then the current increases, decreases, or stays the same?
Stays the same.
No, I think you guys are messing up this a little bit. Yesterday when we looked at the lab, remember we said there was one phenomenon that was so strange because we could change the resistor, but what happened to the current throughout the entire circuit?
It's dependent on the resistor or voltage.
No, but does the current change values throughout
No,
the circuit, or did it stay the same in the entire circuit?
Same.
Right, Max? So it stayed the same. So that's one property about circuits in series. So all the current at the source, and if we're to measure the current at the first resistor and the current at the second resistor, these are all going to be the same value. Right, so if we have 2 amperes, we still have 2 amperes and then 2 amperes. So the current stays the same in a series circuit. And we saw that from the simulation, if you recall. What about the voltage? The voltage at the source. What happens to the voltage as it goes around the circuit? What has to be true? Think back to Kirchhoff's voltage law. What do we say about all the current, about all the voltage that's gained at the power source? What needs to happen to it?
Has to dissipate.
Oh, yes, yes, yes. So we could set up a mathematical formula. So all the voltage at the source has to be used up in the circuit, but because in that circuit we only have 2 resistors, it's going to be the sum of the voltage lost in the first one plus the voltage lost in the second resistor. Because that keeps in Kirchhoff's voltage law. So all the voltage gain equals to all the voltage drop. And the only 2 drops that it had is the V1 and V2. Did that make sense?
Yeah.
Okay.
So the second formula is to calculate the voltage, and the first one is for what again?
Current. I
So the
I is current.
doesn't change throughout the circuit.
Say louder.
The current does not change throughout the circuit.
Yeah, when you connect the circuit in series.
Okay.
But now if we were to look at the second type of circuit, if we look at the current from the source, what happens when it meets a junction?
Oh, does that mean at the second junction it becomes a quarter of the original one?
If there was to be a second and all the resistors are the same along each one. So there's a lot of conditions for me to say yes for the. But if we just focus on this particular circuit, at the junction, assuming that the resistance is the same along both of the branches, then the current will split 50-50. But in general, one way you can get around not knowing how much it gets split by, you could say that all the current at the source will be the current going through the first branch plus the current going through the second branch. So does that explain it better mathematically?
Yes.
Right, so if we go back to our example about 2 amperes, 2 amperes, and in one branch we could say one of it and the other 1 amp, assuming equal resistance. So this is in accordance with Kirchhoff's current law. And what happens once the junction ends and it recombines? How much is the current going in there?
The same one at the beginning.
Yeah, so the 2. All right, so now let's do the same analysis, but now we're going to focus on the voltage. So the voltage at the source, how is that going to be related to the voltage at the first resistor and the second resistor?
The voltage of the first and second resistor is the sum of the voltage source.
Let's go back to the one in series. So the voltage source, you can think of the voltage being carried by the charge. So we have one charge moving along the wire, and at the first resistor it drops off some voltage drop. Now it has less, and at the second voltage drop it releases the rest of the voltage. So that's why we said the sum equals to the source. So all the voltage gain equals to the sum of the voltage dropped.
What does V1, V2 represent again?
Voltage at the first resistor and then voltage at the second resistor. And again, resistor is just a light bulb. A light bulb.
But that's not how it works because it's a circuit, so everything is the same throughout.
No, the current is the same, but as the current goes through different resistors, it's going to lose some energy. Because remember, what do the resistors do? They take the energy.
Could you verify this for me? So V1 has less voltage than V source. V2 has less voltage than V1 and V source. Is that correct?
In most cases, should be correct. But if we assume equal resistance, so if we assume that the light bulbs have equal resistance, then actually the voltage gets split 50-50 as well.
Oh, so if you have 3 light bulbs, then it's split by 33%. If there's 4 light bulbs, it's split by 25%. Is that correct?
Yeah.
Then why do light bulbs in series, they get less and less bright as you go on?
That's why, because if you're splitting it up, they have less energy. And you have less energy means you're not heating up as much, and if you don't heat up as much, you don't glow, because you need the energy due to heat to glow.
Yeah, but you just told me that that it's split equally the voltage.
Yeah, so for example here, if we start off with 6 volts, and the first resistor will be 3 volts and the other one will be 3 volts as well. Right? But if you keep on going down, if you keep on increasing the number of light bulbs, then the voltage has to be split even more. So the voltage goes less and less and less. In other words, the energy that gets absorbed by any one light bulb is less. So it doesn't glow as brightly.
So if there's a third light bulb here, that third light bulb will have 1.5 volts. Is that what you're saying? Or will it have 2 volts because you split 6 into 3? Or do you split the half into 3 into one more?
What's 6 divided by 3? 2. So each one will have 2.
So if there's 3 light bulbs, will it be first light bulb has 3 volts, second? I don't get it.
No, that's the part about charges. They don't discriminate. They split so equally, kind of like Communist Party. It's really good.
Yeah, but if it splits equally, shouldn't they be equally as bright? But that's not the case, is it? Good if it's split equally. If you put 4 light bulbs, they get increased. They decrease in brightness as you go on. But right now, you're telling me that the energy is split completely equally. So why is the brightness different?
Why is the brightness? You know what? We could do this on the simulation, and then that way we could do the circuits, and then we could see the brightness. So we can verify it. So maybe we can do that tomorrow. So that let me just finish up this lesson, but then we could look at that part tomorrow. So that way you could be convinced even more. Yes, it's okay.
Okay.
Yep.
Chun Yu, he asked us a question. Does voltage split on the wire or just the bulbs? Does voltage split on the wire? We assume that the resistance along the wire is 0, so none of the energy gets absorbed by the wire. All of the energy gets absorbed by the light bulb. Okay, so if we look at the one connected in parallel, let's say once again we have 6 volts at the source. But remember, what is carrying the voltage? A charge. And as the charge travels through the circuit, there's going to be a junction. So if one charge goes through one path, how much voltage does it carry with it? So again, at the battery, the charges are getting energy. The amount of energy they gain depends on the voltage. So sometimes what people do in electricity, they think of voltage as energy. Not entirely wrong, but not entirely correct either. So at the battery, you can think of this as a charge getting 6 volts of energy. And it carries it along, and because at the current, when it meets a junction, what happens to the current? It splits. So this charge that's carrying 6 volts goes through one branch. So how much voltage is it carrying with it? Was that too complicated of a question?
I heard a lot of words, but I don't understand.
Yeah. Let me try one more time. So charges are the carriers of energy. At the battery, the charge gets 6 volts of energy. So it's going to travel along, which is what current is. It's traveling along. Now, when it meets the junction, let's say it goes down path 1. How much voltage is it carrying with it? Did it get rid of some, or is it still carrying the 6 volts?
So carries the 6 volts.
Because what's the only way that it can lose some of the voltage? When it meets a resistor. Has it met a resistor yet?
No.
No. So the charge,
Bulb not resistor.
we're assuming that there's no resistance along the wire.
I mean the light bulb.
Yeah, the light bulb is a resistor. So in other words, because it hasn't encountered a resistor yet, when it goes down through path 1, it's still going to carry with it 6 volts. But if instead another charge went through path number 2, how much voltage did it carry with it? 6 voltage as well. So in this case, the voltage going through the first path is equal to the voltage going through the second path.
So voltage doesn't split, only amp split.
Yeah, because the current splits, but then the current was carrying with it, for each coulomb, it had 6 volts of energy. So it didn't use it yet. It just got split of how many are carrying 6 joules of energy. So let me think about this. 2 people each carry 6 joules of energy.
Oh, Mr. Morales, is that why light bulbs in series are dimmer than light bulbs in parallel? Because in series they share the voltage, whereas in parallel they use the same voltage for each light bulb?
Wow, excellent observation, Max.
Oh, sorry, I wasn't listening. I was trying to write this other way of thinking about it. So remember, coulombs could be like, you could think of it like people, because they're carrying that energy. Each one is carrying 6 joules of energy. If one person goes through one path, how much energy are they still carrying with them? 6 joules. And then the other one, that person was still carrying 6 joules of energy. So this one person still has 6 joules of energy. Does that make sense? Because remember, the charges are the energy carriers, and all current measures is how many carriers go through one branch over the other. So what can we say about the voltage at the source? It's going to be equal to the voltage going through the first resistor, and that's going to be equal to the voltage through the second resistor. Ciao, does it make sense? You've been kind of quiet, Josephine too.
Yes. So like in a series circuit, like if you keep adding light bulbs, what do you call it? It will get dimmer because the voltage is less. But then if you in the parallel circuit, no matter how many you add, the voltage is the same, so it's the same brightness. Is it?
Sure, you can think of it that way.
Okay.
Will the amps affect how bright a light bulb is?
Yes.
Yeah, because remember, yesterday we said you cannot separate the 3 from analysis: voltage, current, and resistance.
I do what I want.
All right, Jazz, what about you? Did you follow along for the parallel circuit?
Kinda. I don't really understand some of it, but yeah.
But do you understand why the voltage is the same?
Because it goes through the resistors and then he has to come back to the voltage, the source, right?
Mm-hmm.
Is that right?
Yeah. That's another way of thinking about it.
Mr. Morales.
Wait. I want to focus on this part that Jazz said, because that's another way of explaining this. So when you create a parallel circuit, you could think of it as 2 series circuits. One in red, and in that one, you only have 1 light bulb and 1 battery. And then you could think of it another path as the blue one. And in this one, all the voltage that it gained has to be dropped. So you can think of this parallel circuit as 2 series circuits. So you have a blue path or you have a red path. But because Kirchhoff's voltage law, all the voltage you gain has to be dropped along that particular path. Was that what you were thinking, Jazz?
Sorry again?
So the parallel circuit, you could think of it as two circuits in series.
Yeah, exactly.
So in one path, which is the blue one, you still gain 6 volts, but you have to lose 6 volts. If you consider the red path, you still gain 6 volts and you have to still lose 6 volts. So that's another way of thinking about this.
Wait, so if the voltage source is 6 volts, right, and then it has to go to the first resistor and the second resistor, do both of the resistors get 6 volts, or do they like divide amongst themselves?
No, because remember, you have to think of the blue path separate from the red path. So now the blue becomes its own circuit, and the red becomes its circuit. And what do we say about a closed circuit? All the voltage gain equals to the voltage dropped.
Okay.
So if you're up 6, you have to lose 6.
Okay, alright.
For the blue one, you're up 6, you have to lose 6.
Yeah.
Normally I don't explain it this way, but then you got it in this way, so I'm gonna go for it. It confuses a lot of people though. So now Josephine, she's lost, I think. That's okay. Oh, we have some activity on the comment section, so let's see what's going on there. Will the parallel one run out of battery faster? Oh, you know, I never thought about that. I don't know how to answer that. I don't know. Maybe, right? Because it's using more, but the current's the same when they add up. That's a good question, Ian. I don't know. I'm not gonna lie. I don't know. So I'm just gonna pretend I didn't read the question for now. But maybe find out and tell us tomorrow. Yikwe, you still with us?
Yeah.
Okay, good. Okay, so now let's try to summarize this a bit. So we have series and parallel. And in series, the current stays the same. And for the voltage, it gets share. But in parallel, the current splits. But the voltage stays the same. And now what we're going to do, we're going to take this one step further by considering the resistor. But we know there's a connection between resistor, current, and voltage. So that's due to Ohm's law, which was V equals to IR. So what we're going to do now, we're going to label this as equation 1, equation 2, and Ohm's law, let's call it equation 3. So we're going to substitute equation 3 into 2. Are you following along? Okay, good. So again, instead of voltage, we're going to write current times resistance, because that's what it's equal to. So it will be I source and R source equals to I1 R1 plus I2 R2. I'll give you a moment to look at that. And Now we're going to use equation 1. What conclusion can we make from equation 1? That all the current is the same in a series circuit. So we can divide both sides by I source, and that will cancel out all the current on the left and on the right. So this gives us a new formula. The resistance at the source is the sum of the individual resistors. So as a quick little example, let's say that we have two light bulbs or resistors, and this first resistor has 1 ohm and the second one has 2 ohms. What's the resistance in this wire, the total resistance? Well, if they're connected in series, we just need to add them together. So that would be 1 plus 2, which is 3 ohms. So that's what we're going to be looking at next. So how to analyze circuits and how to get quantities from a circuit itself. So when you have two resistors connected in series and you want to find the equivalent resistance, in other words, the total resistance, you just simply add them together from our new formula. Were you able to follow that? Because we're going to repeat the process. So if you don't get it the first time, you're not going to get it the second time. Yeah, that's where we're going next. We're going to look at the parallel case. Okay, so let's give our equation some names. So this could be equation 4, and this is equation 5. So we're going to use Ohm's law again. So we're going to substitute equation 3 into 4 this time. But if you notice, equation 4 is in terms of current. So what do we need to do to equation 3? We're going to have to rearrange it. You equate? Yep.
Yeah, I'm eating, man.
I'm having tea. You know, my neighbor always asks me all the time.
I'm having lunch.
Oh, my lunch was so bad, Yukui. I was telling you guys, so bad.
Yeah, I know the food panda. Yeah, I'm listening. It's just I'm eating. I can't keep speaking when I'm eating.
Hey, Mr. did you have tacos for lunch?
No, tacos was an example. I had something similar to tacos. Actually, you know, tacos came from the Middle East, so I was having the cousins of tacos.
So, yeah, is it tacos in your blood? Why don't you make your own tacos?
No, because my partner, she's Middle East.
Okay, and?
So you're eating a fusion?
No, because she cooks.
You forced us here, right?
No, we're not trying to like take down the gender patriarchs. Like just trying to live a normal life, man.
Forced her in the kitchen.
Okay. Now, this new equation 3 is rearranged, and we're going to substitute that into equation 4. So what that looks like is going to be V source divided by R source equals to V1 over R1 plus V2 over R2. But now, what can we conclude out of equation 5? All the voltage is the same when the circuit is connected in parallel. So we can cancel it out on both sides of the equation by dividing by the voltage. So the formula that we get is 1 over the R source equals to 1 over R1 plus 1 over R2. So this is the new formula we're going to use. Okay, so as a quick example, what will be the R source in this particular configuration?
Is equal.
Oh no, don't put the number. People don't understand the number. You gotta go through the steps. So 1 over R source will be equal to 1 over 1 plus 1 over 2. What's 1 plus 1 over 2?
4.
4? No, this is not 1984. Wait, is that what you're referring to? Like in 1984, you have to believe that 1 plus 1 is 4.
Oh.
No, okay. Talking to myself. Okay, and how do we isolate for this formula now? We can do cross multiplication. Maybe I should show you in the next slide. So let's go to the next slide. And here we can do cross multiplication. So 2 equals to 3 R source. Then divide both sides by 3. Which gives you R source equals to 2/3. How much is 2/3? I don't know. Whoa, Mr. Tam will be so proud of you, Josephine. Yeah, that's right. So that's why this is known as the reciprocal. So to do the reciprocal and you want to isolate for it, you're going to flip it. So R source equals to 2/3. But I know a lot of people that didn't study with Mr. Tam, so they're more like my style. We do the cross multiplication method. This is like the bourgeoisie style, very technical.
2/3 what? That makes no sense to think about it.
No, that's just the value of the total resistance that you were going to find along the circuit.
2/3 of an ohm?
Yeah.
Why is it less than what?
Yeah, so that's why when you set up things in parallel, it's better than you setting up things in series.
Yay.
Which is why if you're trying to set up your home, you want to have as many parallel circuits, because if you have your home connected in series, that's not very efficient.
And then what about the electric bill?
Say it again, Yukwe?
What about the electric bill?
The electric view?
Does it use up more energy if it's parallel circuit?
Oh, is that what Google found for us?
Yep. We have no one to trust but Google.
Yeah, you know, that's your generation, right?
Yep.
You use more energy, but at least like your stuff is working, at the max level.
Actually, I didn't know that. I suspected that it would be in parallel, but I couldn't make it official. I didn't want to be caught with a lie.
I have a question, Mr. Morales.
Yeah?
I might be a genius, I might be thinking too much, yeah? So, if you go back to slide 4 in the parallel circuit, if you add up all the ohms, right, that's 3 ohms, right?
Yeah?
And then you have 2 resistors here, and that makes 2/3. So can I just add up all the ohms, make it the denominator, and then put the amount of resistors as the numerator? Would that work as a shortcut?
No, dangerous move, because here I'm showing you a very simple setup. But in the circuits you're going to get in the homework questions, you get more complex configurations.
Fine.
Now, we still have a couple minutes, so let me just show you one more thing. So I'm on slide 6 now. Okay, so you're going to see commonly written to find the total resistance in the circuit. That's the same thing as finding our source. So your goal is to try to find an equivalent circuit such that you're only considering as if you only had one resistor connected to a battery. So what this means is that we're going to take our mixed circuit and we want to create equivalent circuits and eventually breaking it down so that it resembles the battery with a single resistor. So what I mean by that is to find the equivalent of two resistors at a time, you consider the ones in parallel first. So how do you find the combined effect of these two circuits combined? Not circuits, of these two resistors combined. The formula that we're going to use is going to be 1 over, sorry, let's give this some names so it'll be easier. 1 over R23 will be the sum of 1 over R2 plus 1 over R3. They're reciprocal formulas. So this is 1 over 1 plus 1 over 4, which is, oh, I should have picked easier numbers. 5 over 4, right? Yeah.
Yes.
And then we do Josephine's trick. We do the reciprocal, which would be 4 over 5. So when we consider these two resistors at a time, we can draw a new equivalent circuit. Where it treats the previous two as a single resistor. So R1 we didn't change, and 2 and 3 we consider the equivalent as R2, 3. Remember, was the goal to think of this as a single resistor. So how are you going to consider these two together? How are they connected? Those two are connected in series. So the resistor equivalence of considering 1, 2, 3 will be R1 plus R2, 3. So 2 plus 4 over 5. Oh, why did I pick such a complicated number? 10, 14 over 5? Josephine, is that correct? So again, it becomes kind of like Sudoku, you know, the puzzle game where no matter what the circuit you have, usually you consider two at a time, starting off with the parallel branches. And you want to find the equivalent circuit such that you're going to find the total resistance by considering all of the resistors as a combined effect of a single resistor. So you consider two at a time, you keep on drawing your equivalent circuits until you find the total resistance.
Can we use decimals instead of fractions?
Yeah, no problem. And you may be wondering, sir, this is only one example. I need to see more examples. Where can I see more? Good thing you're all subscribed, right?
Of course.
So this is my shameless pitch for you to watch the video. No, actually, you should watch this video. I do go over some more examples, so that way it's going to be better for you. And it's the second last video you're going to watch with me anyways, because the class is almost finished.
Do you monetize your videos?
No, you need a lot of watch hours and a lot more subscribers.
You need view box.
Which one?
Viewbots.
What is that?
Oh, it's robots from Russia that watch your videos.
Oh, no, I don't want to cheat. If you have to cheat, then you don't feel like a true victory, I think.
Oh, but you're a capitalist, right? Anything for money.
Yeah, but I'm an ethical capitalist.
don't exist.
That's contradictory.
Paradox.
It's like social democracy, right? I mean, if we're all making jokes, I could have a joke too, right? All right. So once again, the homework, try to watch the video so that way you get more familiar with these examples. This was 11.8 from the textbook. Tomorrow is the last lesson for this unit, and we're just going to be analyzing circuits for voltage, current, and resistance. So tomorrow is going to be more calculations. So it won't be a lot of me talking. We're actually going to work together and solve some questions, okay?
Okay.
All right. Yeah, hopefully tomorrow, please eat a little bit earlier because you didn't have a lot of energy today. So it wasn't so exciting for me to teach today. So get some energy for tomorrow. It's our last day together.
Okay.
Do you have any tips to study for the final exam?
Yeah, but then let's finish this unit first, and we could focus on the exam after.
Okay.
Okay.
Don't worry, I got you guys. Bye-bye.
Bye. We can go now?
Yeah, finish. It's 2 o'clock.
Thank you.
Bye-bye.